So today we're going to learn what machine learning is, and we're going to do some machine learning on a real data set. And more specifically, we're going to do a decision tree and a random forest, and possibly something else if we have time. But who am I? Hi, I'm Leo Glowacki. I'm a fifth year here at OSU, double majoring in data analytics and music. I'm the BDA education director. I'm a certified art studio instructor. So what is machine learning? Well, it's basically computers learning from data, but more formally, you could say it's an application of artificial intelligence that provides systems the ability to automatically learn and then improve from that experience, but without explicitly programming it. And so why would you use machine learning? Well, there's several reasons, but some of the top ones here are that you don't have to explicitly program anything. A lot of times, if you want some sort of result, you have to go in and you have to program some sort of formula and come up with all the relationships between everything. But with machine learning, you actually just use data and it will figure out the relationships between those or what needs to happen. And most of the time, it's actually more accurate, and it's also easier since you don't have to explicitly program all of that. And it's especially helpful when problems are too complex to sit down and explicitly program things like that. And also when the environment changes over time, as long as new data is also being fed into the machine learning algorithm, then it will automatically change and update itself instead of having to reprogram every time something changes in the real world. So this goes off of sort of what I just said. We have here on the left our traditional programs, which are our data, and we write by hand this static code that does these things, and then we get our real world result. But with machine learning, we don't have this static code here. We have our algorithm, which can generate a hypothesis about how things work. It can give us a real world result. Well, it doesn't. We look at the real world result, which gives us feedback, and we kind of go through this feedback loop to tweak our algorithm and get more accurate hypotheses and results. So what can machine learning do really? Well, one thing that it can do is it can sort, is this spam or not? Another thing is the people you may know algorithm is run by machine learning. Self-driving cars. When you get those fraud alerts on your phone, like, hey, did you just buy this thing? Because it doesn't look like something you'd normally buy. And I guess, well, I had to say ALEXA, otherwise mine's gonna go off. So there's that as well. And also the Google DeepMind's AlphaGo can also play Go and defeated the world champion in 2016. So how does machine learning work really though? In a nutshell, if it looks like a duck, swims like a duck, and quacks like a duck, then it probably is a duck. But what do I really mean? So basically machine learning would look at all the ducks, and then it would look at what you want to figure out is a duck or not. And based off ducks that it's seen, it can tell you if that's a duck or not. So with machine learning, we usually go through this process of we get our data and we use our data to build a model, and we go through this whole model building process that we're not going to get to here. And we generate our final model from it. And then when we have our new data and we have our final model, we can use those to make a prediction about our new data. So for example, is this a duck? Well, obviously, but so this here would be our new data that we want to make a prediction on. And so we need our data. So we need two things. We need ducks and non-ducks. So we would gather our ducks. We would give it all these photos of ducks. And we want to, generally speaking, we want a large variation in our data that we give our machine learning algorithm so that it knows all the instances of things that it might see. So like if we only gave it pictures of ducks like this, but then not of duck butts, if it gets a duck butt, it's going to say that's not a duck. So it's important to get a wide variation of data. But we also have to say what isn't a duck. So if we give it something that isn't a duck, it'll know that, hey, that's not a duck. So that's not a duck. Also not a duck. Kind of looks like a duck, but not a duck. This one really looks like a duck, but it's just like a gourd or something. Also not a duck. So we take our ducks and our non-ducks as our data. And then we want to build our model. So in this simplified example, we're just going to say that our model is something like if ducks have 2 feet and 2 wings and that are with these kind of feathers and a bill that looks like this, then it's probably a duck. So, you know, if it looks like a duck, and then we could also add in our model if it quacks like a duck, etc. So that's our model. And then we can use this model to make a prediction. So we give this to our model, and then it will say, ah, yes, this is a duck. So just as an overview, we have our data, our ducks and our non-ducks. We feed this data into our model building process. And after some model building process magic that we won't get to yet, we get our final model, which says what a duck is. And then we can test it and say, okay, is this a duck? And it will say, yeah, this is a duck. So there's 3 main types of machine learning. The example that I just did is supervised machine learning because it's labeled data. We said, here's things that are ducks and here's things that are not ducks. And those were our labels. And typically supervised machine learning either classifies items, so duck or not duck, or predicts numbers like next quarter, you know, how much are we going to have in profit? And so we could say, oh, well, next quarter we'll have about $10 million in profit. Then there's unsupervised machine learning, and that's typically things where we're just grouping things together and finding patterns or anomalies. And we just want to know, you know, are these things similar? Are they not similar? And that's a lot of the times because we don't have labels on that data, and we can find interesting patterns that way too. And then there's also reinforcement learning, in which that's like how an algorithm learns to react to an environment. So like in this photo, the robot is like, does this work? You know, will it go in this, will this sphere go in this circle here? Or, you know, will it go in the square? And that's used a lot in like typical AI applications and things like that. And not as much currently in data science, so we're not going to talk about that too much today. So here's just like another way of looking at everything that I just told you, basically. There's machine learning. There's 3 main types: supervised, unsupervised, reinforcement. And supervised learning normally does classification, which is like duck or not duck, and regression, which is like how much profit are we going to make next quarter. And then there's unsupervised learning, so we can cluster things together, and dimensionality reduction, where we reduce the number of variables but still getting approximately the same amount of information. And then there's reinforcement learning, so things like robot navigation. So tonight's data set we're going to work on is the same one from last week's EDA workshop. So I'm not going to go too much into detail since we talked about it last week. But if you weren't there, basically it's just data on student performance in some Portugal schools. And we want to know, based on this demographic data that we have of these students, can we predict how well they're going to do? And what are, if we can, what are things that actually predict how well that they're going to do? So just to make this a little more explicit than last time, we're going to use R Studio and some R packages today. R is an open source programming language that was built by statisticians for statisticians. So a lot of things in R just make sense for doing that kind of work. R Studio is a free integrated development environment, or an IDE. Basically, it's where you code in R. And our packages are collections of our functions, compiled code, and sample data. So basically, packages are boilerplate code, things that you're going to want to use again and again and again. And so today we're going to be using a lot of machine learning packages. So we don't actually have to write all the code for the algorithms and models ourselves. We're actually just going to use these packages that have been built and verified by teams of other people. So let's get the code. So you'll see Enan went ahead and put the instructions in the chat. But basically, we'll go to this link and get the code. It's the same link from last workshop. And you can log in with your account from last week or create a new account if you haven't made one. And you'll see for this one, we have the ML Bootcamp. Bootcamp was from the last one. Excuse the poor labeling. I probably should have named it EDA Bootcamp. But so tonight is ML Bootcamp. So you'll open that up. Make it full screen. And it's going to take a second to load, but just be patient. Okay, so you should see a tab for files. And if you click on mlworkshop.rmd, you'll see the file that I pre-made for this workshop. And we have this all here. Also, is my code readable for everybody on my screen? Cool, thank you. So you'll see this first chunk, this code chunk here, is just a lot of setup. And just to explain it a little bit, all of these library calls here, the library parentheses, and then the library name, all of this is just to get the libraries that we're going to use in tonight's workshop. I import the data here, and I create a couple additional variables for their final grade. So we get it in a pass-fail format and a letter grade format. And mostly tonight we'll be looking at the letter grade. If you want to learn more about how to do the things that I'm doing here, I'm going to link to a resource at the end, and so I'll mention that there. So don't worry if you don't understand all of that. Okay. So then if you remember back to our picture of the model, we had our data, and then we had our new data that we wanted to predict, was that a duck or not a duck? So our one duck picture. And so what I'm doing here in this second code block is I'm taking our full data set, which is student underscore poor for their student Portuguese grades. And I'm just removing 10 students from this data set to use as our new students. So later we'll predict with our model these students and see if we got it right or not for these 10 students. And then I need to remove these 10 students from our full data set so that we don't train our model on those students. Because if we show these students to our model and then we ask it to predict, it's kind of like cheating because it's already seeing those students exactly. So the first machine learning model that we're going to build is going to be a decision tree. And decision trees are a type of supervised learning. So we use them when we have labeled data. And you can use them for classification or regression. So you can use them to say, is this a duck or not? Or you can use them to say, you know, approximately how much profit are we going to make next quarter? And they work like a series of questions. So if you'll see on this engineering flow chart, we can figure out whether or not we should use a hammer, or if there's no problem, or if we just need to use an insane amount of duct tape. And this is basically what decision trees look like. It's just a series of questions, usually yes or no. And decision trees, even though they're they're simple, like you look at them and you're like, okay, that's pretty easy. Is that really machine learning? Like, okay, but they're actually pretty powerful. They can fit complex data sets, and in the way that they fit it, we can see what's important about the data set. And that makes them white box because we can see what's going on. We can look at the model and understand what's actually happening. Whereas things like neural networks are so incredibly complex that us humans with our little tiny brains have no idea what they're doing under the behind the scenes. And decision trees also don't assume too many things about the data. So it's really nice because you can almost just slap a decision tree onto any data set and not worry about how the data looks too much. And perhaps best of all, they're the backbone of random forests, which we'll get to in a bit, but random forests are very powerful. So here's another example of a very simple decision tree if you want to figure out what Harry Potter class you might be. I'll let you decide that for yourself. So let's do decision tree here. So I've gone ahead and I've done the full code here for decision tree. So actually, how to run, well, I know last time we used the knit button a lot, but this time I think it makes a little more sense to run the code blocks individually. So to run code blocks in our studio, you'll hit run current chunk and make sure to start at the first block so you can load this in. And you should see after running the first code chunk that here in our environment, we have our student poor, our data set is loaded, and we can see that it has 649 observations of 35 variables. So that's our 649 students. Then if we run the second block, we'll also see that we now have our new students data of our 10 students that we want to predict their grade. And then our student Portuguese data now has 10 less observations since we removed those new students from the full training data set. Okay, so here is where we are building our decision tree. So I'm just gonna write a comment there. It doesn't do anything to the code, but it's just easier to tell that that's what that's doing. So here we're taking our decision tree. We're just creating a variable named dt_model to stand for our decision tree. And we're gonna use this function train. And this train function takes a formula, it takes a data set, and it takes a method. And it's from the carrot package, which I will link a resource to at the end. And so a formula is basically what we want to predict. So we want to predict the letter grade. And then a tilde, and everything that we want to use to predict it. So with separated by plus signs. So all of these variables here, school, sex, age, address, etc., are the other variables in the student Portuguese data set that we want to use to end up predicting the letter grade, except for we're not including G3 or pass fail because those are one and the same. G3 is the final grade. Pass fail is whether or not the grade is above 10 or not, and the letter grade is based directly on the numerical grade. So not including G3 or pass fail, this formula has all of the other variables. I'm going to use that to predict our letter grade. We give it the name of our data set, student port, and as a note, these are all the exactly the variable names. So letter grade is what we're going to predict. So it's there just like that. And then the rest of our variable names as well. So here's where things start to get a little bit more interesting. We have method, which is equal to our part. And that stands for our partition. And it's because decision trees sort of go through and partition things. And then we'll print our model after we make it. And so we'll run that by clicking up in the top here. And okay, so we see that we had 639 samples that we used, and that makes sense. 32 predictors. So our predictors are all of these variables here that we're using to predict letter grade. And letter grade has 5 classes, A, B, C, D, F. It says all of this stuff here is part of the model building process. And out of all this model building process, it automatically for us selects one model that it thinks to be the optimal model, which is the model with CP equal to 0.13. So this one here. And CP stands for complexity parameter. And that's just basically how complex is the model. So out of the 3 models that it tried here, it actually picked the simplest model. And it decided that, and you'll actually see as we are building more complex models, our accuracy actually went down. And so the simpler model here was actually the best model in terms of accuracy. And then if we run the next code chunk, we can actually plot this decision tree. So we can actually see here the decision tree that it made. So the way to interpret this graph that it made is at the very top is the prediction for each group. So looking at all the data here, 100%, that's what that means. 100% of the data, we would if we had to guess what somebody's grade would be, we would say D. And that's because most people in the data set, 31% of the data set here made a D. That's a lot of people making Ds. But so the decision tree then said, okay, well, let's get this a little more fine-grained. If let's say if their G2, their second term grade is greater than 12, then I would predict actually C. So if and this accounts for 49% of the data here. So 49% of the people in this data set had a second term grade of greater than or equal to 12. And out of those people, 37% of them scored a C. And so we guess just if we know somebody made 12 or higher on their G2, their second term grade, then we would guess, okay, they probably, most likely they made a C. Although it's also pretty fairly likely that they made a B or even an A, and nobody failed actually. So if we would always guess using this model, if somebody's G2 was greater than or equal to 12, we would be pretty confident that they probably didn't fail. And then it actually splits on this same variable again, G2 greater than or equal to 14. And so if their grade is equal to greater than or equal to 14, the second term, then they're probably going to make an A, maybe a B, but probably an A. And if it's less than 14, then they probably made a C. And we're predicting C again here, but it's a little more accurate, as you can see, because if you look at the probability distribution here versus here, so at this time we have 70% of the people in this group made a C versus 37 made a C here. And consequently, if their G2 is less than 12, they probably made a D, and they could have failed too. So you'll notice we gave it all of these variables, 32 predictors in total. And the decision tree that it gave us only used one variable, and it just used that one variable twice. And it could have used this one variable a lot of times. You know, we could have maybe said, okay, well, what if your G2 grade is less than 5? Then you probably failed. But we don't see that. Why? So this has to do with the way that decision trees are made and grown. And so there are actually ways that we can get different decision trees. This is not the only decision tree that could be built for this data, but with the default ways of evaluating models and what the best model is that are built into this function, this is the decision tree we get. So now that we have our model, we still have our 10 students that we want to try and predict on. And so if we run this here, we can see our top row is us predicting using our decision tree model that we just built. We're saying, what are the new students' letter grades? And then we also look, the second line is actually, what are the new students' actual letter grades? So the top line is our predicted grades, and the bottom line is what they actually made. And you'll see, you know, it's not too far off. It's not perfect. There are a lot of mistakes, but when it does make a mistake, it's only one letter grade off. And if we do scroll back up and look at our accuracy for our sampling when we were building the model is around 63%, which, yeah, that's, you know, that's okay. Not really, you know, it's not really great. But if you do take into consideration the fact that when we're wrong, we're most likely, most of the time, only off by one letter grade, then it's not so bad. So yeah, but what if, you know, in some respects, this isn't the most useful model though. And that's because actually we're using a student's second term grade to predict their final grade. I kind of feel like that's cheating just a little bit. What I want you guys to see is go in and see what happens if you delete G2, or what happens if you delete G1, or what happens if you delete both of them, and rerun this model and rerun the graph and see how the accuracy changes and see how the graph, the decision tree itself changes. And if you have time, you know, I encourage you to just try maybe even just like 3 or 4 variables out of here, just randomly selected, or things that you want to see create rules, you know, so like based off of someone's family size and their health and their absences, you know, how well, just using those 3 variables, can we predict what their letter grade might be? So the next thing we're going to talk about is just random forest and ensemble learning. And so there's a lot of different kind of ensemble learning models in machine learning, but they all follow the same principle. And it's basically just taking a bunch of models and combining their predictions into one prediction. So it's kind of the machine learning equivalent of asking your one friend that you know is like an expert in the field some sort of question, or asking like 100 people this question and getting their response, and then taking the sort of average of all of their responses. So a random forest is one type of ensemble learning. So it's a bunch of decision trees, and each decision tree is trained on a random subset of the features or the predictors. So in this instance, it would train on like school, sex, and age. One of them would be trained on those, and then another one could be trained on their mother's occupation, if they lived in a rural or urban area, or something else. I can't remember all the variables in this data set. And it also uses a random set of the training data points for each decision tree when it's being built. So instead of using all 639 students when we're training each tree, we're using a random subset of those for each tree as well. And then our final prediction is just a majority vote of the predicted class. So if we build a random forest with 100 decision trees and 51 of those decision trees say the student made an A, 18 say the student made a B, and C said 10, et cetera, with lower numbers, then we're going to predict A because it had the most votes. So they're very democratic in that way. So basically, you know, our random forest is a bunch of decision trees. Each of these decision trees are a little bit different from one another because they were built using slightly different predictors and slightly different subsets of students for our data. And they each say one class. So in this example, this tree said A, this tree said B, this tree said B. So we would say probably B. So if we go back to our code, we have here our code for a random forest. And what's actually really cool about this carrot package that I mentioned earlier is this code for the random forest is exactly the same as the code for the decision tree, except for the method. And it's this also like slightly cryptic looking method, ranger, which I'll explain just a little bit more in a bit. But this basically means that this method is going to make a decision tree. And so if we run this, you're going to see this actually takes a little bit, it takes just a little bit of time. And that's because this is building a bunch of decision trees. So naturally, it's going to take some time. And not only is it building each individual decision tree, but it's also in the background testing a bunch of the individual decision trees. So it is a little bit computationally expensive. But that's okay because it gives me more time to drink tea. So, well, I'm waiting for that to run because apparently it's going to be really slow tonight. I'm going to explain a little more about that function and how we just changed one thing. So this carrot package is a way of making, it just has a bunch of different machine learning models built into it. And if you look, here's all of the method tags. So again, in this code here, method equals ranger. And so if we search on this page here, we see this is how you know what method you want to use. You look, you say, oh, I want a random forest. And that's how you know, oh, the method is ranger. And let's see, we used, oh yeah, we used our part. For our decision tree here. So as long as you're using the right kind of machine learning, so like if it's, in this instance, since we're doing classification, you could change the code to anything for classification, and it should work. You'll have to probably install another package. But this code that I just showed you essentially allows you to create, I don't know, like 50 different machine learning models, just like that. All you gotta do is change that method tag. So that's really cool about that. Okay, so our decision tree finally finished. And you'll see it tested a bunch of different things that we won't have time to get into tonight. But you will see, let's see, the final values were used were MTRY41, split rule extra trees, and min node size 1. So 41 extra trees. All right, so now our accuracy here is about 73%, whereas our highest accuracy here was 67, or 60, about roughly 64%. So that's almost a 10% improvement, so that's really good. And now we can predict again the same as we did before, but now just using our random forest model to predict. And we actually see here that at least out of the 10 students that we randomly chose, it actually got all of these right. And the only thing that we did from here to here is just build a bunch more decision trees in our random forest model. And the only thing that we had to do to build all those additional decision trees was change this method here. And this may or may not be the best model. There could be a completely different type of machine learning algorithm that would make it better, or we didn't test all of the right different models that there could be. And there's also the argument between how big do we want to make our tree versus how well do we want to be able to read it and figure out what's going on, and overfitting versus underfitting. But this gets into a bunch of things that we just simply didn't have time for in an hour introduction to machine learning. So there's still a lot that we didn't have time to talk about and get into. But then we didn't talk about this whole model building process. I just kind of alluded to it, especially since most of this is happening in the background and we don't have to worry too much about it until we start needing to tweak it. But hopefully you got an idea of how to do machine learning and what machine learning is, and can use this as sort of a springboard into further things if you want. So here's some great resources that I recommend if you want to get further, and I'll actually send this in the our learning BDAA Slack in a minute. But the Carrot package book is what I was showing earlier, and getting started with R and the R for data science books are two things that'll really help with understanding all that code at the beginning and how programming in R just generally works anyways. And the hands-on machine learning with R book also explains a lot more of the machine learning process and how to choose different machine learning models and understand them and things like that. Questions, great. I see a question from George. Would you recommend learning multiple languages at once for data science? Yes and no. I would recommend trying to just focus on one until you get to a certain level of proficiency and being able to do things with it. And once you get more proficient at it, then starting to learn another language, because it's kind of hard to learn two separate languages at the same time. And at least me personally, I get syntax and things confused a lot if I'm switching back and forth a lot. But at the same time, just with classes and different things for my work and stuff, I end up switching languages all the time anyways. So if you can learn one at once, and focus on it, I'd recommend that. But sometimes in reality, it's just not practical, is my answer. Pretty please fill out this feedback survey. It's pretty short, just a little bit longer than the last one because I am asking a couple questions about the workshop, the bootcamp series in general. But I don't have the rest of the workshops for this semester explicitly planned out. And it's not necessarily because I like to procrastinate, and that's also not necessarily true. But the reason is I really build my workshops off of feedback from you guys. So if you guys could take the time to fill out the feedback survey and let me know things that went well or not so well and what you want to see next. I'm definitely going to be reading that and trying to cater the workshops even more for you guys. So yeah, thank you guys. If you have any questions that you didn't want to ask during the workshop, I'm going to stick around for a bit. But otherwise, thanks for being here. I hope you learned a lot and hope you have a great night.